Hello friends, welcome to my lecture on solution of higher order homogeneous linear differential equations with constant coefficients. So far we considered second order homogeneous linear differential equation with constant coefficients. Now we shall generalize the idea to higher order homogeneous linear differential equation with constant coefficients. So let us consider the nth order homogeneous linear differential equation with constant coefficients a naught by n is nth derivative of y with respect to x plus a1 by n minus 1, a2 by n minus 2 and so on a n minus 1 by 1 plus a n by equal to 0, where a naught, a1, a2, a n minus 1, a n are constant coefficients and pi r denotes the rth derivative of y with respect to x. So, 1 less than or equal to r less than or equal to n. This is the notation for the derivatives of y with respect to x. Now, let us put y equal to e to the power m x. We have seen in the case of the second order linear differential equation with constant coefficients that in the case of first order linear differential equation, it turned out that exponential solution is a solution of that homogeneous linear differential equation of first order. So, we tried why not let us see for exponential solutions of second order, and it indeed turned out that the second order linear differential equation have exponential functions as solutions. So, let us put y equal to e to the power mx in equation 1. So, then what do we have? If you take y equal to e to the power mx, then y dash is m times e to the power mx, y double dash is m square times e to the power mx and so on. Nth derivative of y gives you m to the power n e to the power mx. So, when you put y equal to e to the power mx in equation 1, what you get is a naught m to the power n plus a1 by m to the power n minus 1 and so on n minus 1 m plus a n times e to the power mx is equal to 0. Now, it is very well known that e to the power mx is never 0, okay, for any x belonging to R. So, we will get a naught m to the power n plus a1 m to the power n minus 1 and so on a n minus 1 m plus a n equal to 0, which is known as the auxiliary equation or the characteristic equation. So, this equation will have n roots counting the multiplicity. So, those n roots, if those n roots are all real and distinct, okay. So, there are three possibilities. The n roots of the equation, auxiliary equation, are all real and distinct. Then there is the second case where the sum of the roots may be equal, and then the third possibility where some of the roots may be complex. So, let us discuss each case one by one. So, suppose the n roots of the auxiliary equation are m1, m2, mn and they are all distinct. Then the corresponding solutions of the equation 1 will be e to the power m1x, e to the power m2x and so on e to the power mnx, and they are all linearly independent, because if you take to prove that these n solutions e to the power m1x, e to the power m2x and so on e to the power mnx, they are linearly independent Li. Let us consider C1 e to the power m1x plus C2 e to the power m2x and so on Cn e to the power mnx equal to 0. Then we have to prove that C1, C2, Cn are equal to 0. We can prove this by mathematical induction. Suppose we can prove this by mathematical induction. So, So, the result clearly holds for n equal to 1, the result holds for n equal to 1 because when n is equal to 1, e to the power m1x is never 0. So, the result holds for n equal to 1. So, this implies that e to the power m1x is linearly independent. So, suppose the result holds for k, okay, for k functions, that is then we have to show that the result holds for k plus 1 functions. So, C1 e to the power m1x plus C2 e to the power m2x and so on, Ck plus 1 e to the power okay. So, C1 e to the power m1x plus C2 e to the power m2x and so on, Ck plus 1 e to the power mk plus 1x equal to 0. We have to prove that C1 C2 Ck plus 1 equal to 0. Now, since e to the power m1x is never 0, we can divide this equation by e to the power m1x. So, dividing we have C1 e to the plus C2 e to the power m2 minus m1 into x plus C3 e to the power m3 minus m1 into x and so on, Ck plus 1 e to the power mk plus 1 minus m1 into x equal to 0. Now, the result holds for C1 C2 Ck plus 1. So, whenever and the k functions is equal to 0, now we can differentiate this with respect to x. Let us differentiate this with respect to x, then we will get C2 e to the power m2 minus m1 x into m2 minus m1 plus C3 e to the power m3 minus m1 into x into m3 minus m1 and so on, Ck plus 1 e to the power mk plus 1 minus m1 into x into mk plus 1 minus m1 equal to 0. Okay, so e to the power m2 minus m1x, e to the power m3 minus m1x, e to the power mk plus 1 minus m1x are functions where these m2 minus m1, m3 minus m1, mk plus 1 minus m1 they are all distinct, and we have assumed the result for k functions. So, these are k functions. Okay. So, they are linearly independent. So, their coefficients must be 0. So, C2 times m2 minus m1 equal to 0, C3 times m3 minus m1 equal to 0 and so on, Ck plus 1 mk plus 1 minus m1 equal to 0. Since m2 is m1, m2, m3 and so on, mk plus 1 are all distinct, this implies that C2, C3 and so on, Ck plus 1 are all zeros, and from this equation when you put C2, C3, Ck plus 1 equal to 0 we get, so this equation, let us call it as 1. So, from 1 we get C1 equal to 0. So, C1, C2, C3 and so on, Ck plus 1 equal to 0. So, the result holds for k by mathematical induction, it holds for all k. So, the here the n functions e to power m1 x, e to power m2 x and so on e to the power m1 x are linearly independent, and therefore, the general solution we can write as, so general solution can be written as by equal to C1 e to the power m1 x plus C2 e to the power m2 x and so on Cn e to the power m1 x when the roots of the auxiliary equation are all real and distinct. So, let us say for example, d cube minus 2d square minus d plus 2y equal to 0, d cube minus 2d square minus d plus 2 y equal to 0. D here represents d over dx. So, it is a third order linear differential equation with constant coefficients. So, let us assume y equal to e to the power mx. Then we get m cube minus 2m square minus m plus 2 e to the power mx equal to 0. Since e to the power mx is not 0 for any x, we have the auxiliary equation m cube minus 2m square minus m plus 2 equal to 0. Now, we can easily factorize this equation. So, m square times m minus 2 minus 1 times m minus 2. So, the factors are m minus 2 and m square minus 1. So, we can write m minus 1 into m plus 1 equal to 0. The three roots of the auxiliary equation are 1 minus 1, 1 minus 1 and 2. So, the auxiliary equation has real and distinct roots. So, the general solution will be y equal to C1 e to the power x, C2 e to the power minus x plus C3 e to the power 2x in this case. Okay, now let us move to second possibility. In the second case, we have real multiple roots when a certain root occurs more than once. So, let us say let R be the multiplicity of a root, say m equal to m1, and let us assume that the remaining n minus r roots be real and distinct. So, corresponding to the distinct roots n minus r roots, the corresponding n minus r real and distinct roots, we can write the corresponding part of the complementary function like we wrote in the case of case 1. So, when we have r roots which are equal, how we will find the corresponding part of the complementary function? Let us see that here. Okay, so let us assume that m equal to m1 occurs r times. M equal to m1 occurs r times. So, one solution of the auxiliary equation is one solution of the equation 1 will be y1 x equal to e to the power m1 x. Let us try to find the other r minus 1 linearly independent solutions of the equation 1. So, we shall now show that the remaining r minus 1 linearly independent solutions corresponding to the multiple root m equal to m1 are given by x into y1, that is x into e to power m1 x square into y1, that is x square into e to power m1 x, and so on x to the power r minus 1 e to the power m1 x. Now, let us note that the Wronskian of these solutions W is the Wronskian of e to the power m1 x e to the power m1 x square e to the power m1 x and so on x to the power r minus 1 e to the power m1 x. So, let us first note that the Wronskian of these r functions is not equal to 0. So, they are linearly independent. Let us see how we will prove this. We have to show that these r functions are linearly independent. So, let us consider their combination C1 e to the power m1 x, C2 x e to the power m1 x, and so on, Cr x to the power r minus 1 e to the power m1 x equal to 0. We have to prove that C1, C2, Cr all are zeros. So, since e to the power m1 x is never 0, let us divide this equation by e to the power m1 x. So, we get then C1 plus C2x plus C3x square and so on, Cr x to the power r minus 1 equal to 0. So, we get this equation. Now, we have to prove that this equation gives us C1, C2, C3 and so on, Cr equal to 0. Now, in other words, we have to show that the functions 1 x, x square, x to the power r minus 1 are linearly independent. We have to show that 1 x, x square, x to the power r minus 1 are linearly independent. Okay, so this is a polynomial in x of degree r minus 1. So, and we need to find these r coefficients. Okay, so let us take n points, r points x1, x2, xr, r points x1, x2, xr, which satisfy this equation. So, then we shall have let us say let C1 plus C2 x1, C3 x1 square and so on, Cr x1 r minus 1 equal to 0. We have r distinct points. Let us take r distinct points x1, x2, xr which satisfy this equation. So, then C1, C2, x1, C3 x1 square, Cr x1 r minus 1, C1 plus C2 x2, C3 x3 square, x2 square and so on, Cr x2 r minus 1 equal to 0 and so on, C1 plus C2 xr plus C3 xr square and so on, Cr xr r minus 1 equal to 0. Okay, so this is a homogeneous system of linear equations. We can write it as 1 x1 x1 square, x1 to the power r minus 1, 1 x2 x2 square, x2 to the power r minus 1 and so on, 1 xr xr square, xr to the power r minus 1, C1 C2 and so on, Cr equal to 0. Now, this homogeneous system of linear differential equations. So, this will have a trivial solution provided the determinant of this matrix is non-zero, and the determinant of this matrix is non-zero because it is a bounded determinant whose value is equal to determinant of the this matrix 1 x1 x1 square, x1 to the power r minus 1 this is equal to product of 1 less than or equal to I less than j less than or equal to r xi minus xj. So, since xi's are all distinct, okay, since xi's are all distinct, the value of its value is non-zero since xi's are distinct. So, this determinant of this is non-zero and therefore, C1, C2, Cn are equal to 0. Hence, so these n functions 1 x, x square, x to the power r minus 1 are linearly independent, and so the n functions here they are linearly independent by 1 x by 1 x square by 1 x to the power r minus 1 by 1. So, the proof of W not equal to 0 is a rather difficult. So, we have proved it by the other method. Now, let us see if we let us substitute by, if you define this as Ly, if you define the left hand side of equation 1 by Ly, then what we will have, if you put by equal to Emx in this, okay, then L Emx will be equal to A naught m to the power n, A1 m to the power n minus 1 and so on A n into e to the power mx, and since m1 occurs r times as a root of this constructive equation, we have this can be written as m minus m1 to the power r into gm into e to the power mx, where gm is not, gm1 is not equal to 0, e to the power mx is never 0. So, m1 occurs r times means the remaining expression gm into e to the power mx must not be 0. So, gm1 is not equal to 0. Now, let us consider m as a parameter. So, then d over dm L Emx, let us differentiate this equation with respect to m. When we differentiate this equation with respect to m, what we get is d over dm L Emx equal to r times m minus m1 to the power r minus 1 gm e to the power mx m minus m1 to the power r d over dm of gm e to the power mx. Now, since L is a linear differentiable operator, we have taken L as this, okay, L as this. So, it is a linear differentiable operator. So, with respect to the independent variable x, and m and x are independent to each other. Therefore, d over dm of L e to the power mx can also be written as L d over dm of Emx, and when we differentiate Emx with respect to m, we get x e to the power mx. So, L x e to the power mx is equal to this, and this vanishes, okay, at x m equal to m1, this vanishes at m equal to m1. So, x e to the power m1 x is also a solution of the equation 1. Okay. So, since the right hand side vanishes at m equal to m1, x e to the power m1 x is also solution of the differential equation 1. Again differentiating equation 4 with respect to m, this equation you again differentiate with respect to m, then we will have r into r minus 1 m minus m1 to the power r minus 2 gm e to the power mx, and the other terms will be these ones 2r m minus m1 to the power r minus 1 d over dm of gm e to the power mx, and then m minus m1 to the power r d square over dm square gm e to the power m1 x. Again we put m equal to m1, so this vanishes because r is greater than 2. So, this vanishes and this also vanishes and this also vanishes. So, x square e to the power mx is also a solution of equation 1. So, in this manner we continue, and when we differentiate r minus 1 times, after r minus 1 times we differentiate, the first term on the right hand side is obtained as first term here. Okay. If you differentiate it, if you differentiate this, here we have differentiated 1, we see here, if we differentiate r minus 1 times, okay, m minus m1 to the power r, this expression m minus r minus 1 times, then the first term on the right side will be obtained as r factorial m minus m1 d gm into e to the power mx, which vanishes at m equal to m1. The other terms will also vanish because their powers of m minus m1 will be more than or 1, and here, so x to the power r minus 1 e to the power m1 x will also be solution. Now, if we differentiate one more time with respect to m, that is r times, the first term on the right hand side will be now r factorial gm e to the power mx, which does not vanish at m equal to m1, since gm1 is non-zero. So, it shows that x to the power r e to the power m1 x is not a solution, and thus we find that e to the power m1 x, x e to the power m1 x and so on x to the power r minus 1 e to the power m1 x are linearly independent solutions corresponding to the multiple root m equal to m1. Okay. Now, let us in the case of r multiple roots, r roots of the indicial equation being equal, this is how we will find the independent solutions. So, let us consider the equation at 8 d cube minus 12 d square, and then we have 6 d minus 1 by equal to 0. So, the auxiliary equation will be 8 m cube minus 12 m square plus 6 m minus 1 equal to 0. 8m cube minus 12m square plus 6m minus 1 equal to 0. Let us solve this cubic equation. So here we notice that if we take m equal to half, then we get 8 into 1 by 8 minus 12 into 1 by 4 plus 6 into 1 by 2 minus 1 equal to 1 minus 3 plus 2 plus 3 minus 1 equal to 0. So m equal to half is the root of this equation. So we can put m, let us put 2m minus 1, okay. 2m minus 1 is the factor of this equation, 2m minus 1. So we can write 4m square. 4m square means 8m cube minus 4m square, and then we will take 4m square 8m, not 8m, 4m into 2m minus 1. So we get minus 8m square minus 4m square minus 12m square minus plus 4m. So we get how much we require? 8m cube minus 4m square minus 8m square, so minus 12m square plus 4m so minus 4m, so 2m minus 1, okay. So this is equal, this is how we have factorized this. So this is 2m minus 1 into 4m square minus 4m plus 1. These are the two factors, and this can be this is square of 2m minus 1, so this is 2m minus 1 whole cube, okay. So here m equal to half is the root of multiplicity 3. And so the general solution is y equal to c1 plus c2x plus c3x square e to the power half x in this case. Let us now consider the third case, multiple complex roots. This case is a combination of the two earlier cases. Suppose if p plus iq is a multiple root of order m, then since the coefficients of the given differential equation in one are real, okay, the p minus iq will also be a multiple root of order m. So if for example, if p1 plus iq1 is a double root, then p1 minus iq1 is also a double root. Now we have earlier seen that if p1 plus iq1 and p1 minus iq1 are roots of the auxiliary equation, then the corresponding independent solutions are e to the power p1 cos q1x and e to the power p1 sin q1x. Now p1 plus iq1 is a double root and p1 minus iq1 is a double root. So therefore if by1 is p1 plus iq1 and by 2 is p2 minus p2 minus iq2, by 1 is p1 plus iq1 and by 2 is sorry, if by 1 is e to the power p1 plus iq1 into x and by 2 is p1 minus iq1 into x, then then by 1 plus by 2 is also solution and by 1 minus by 2i is also solution. So if p1 plus iq1 is a double root and p1 minus iq1 is a double root, then e to the power p1 cos e to power then by 1 plus by 2 and by 1 minus by 2i, okay, which are e to the power p1 cos q1x and e to the power p1 x sin q1x. They will also be double roots, and therefore the corresponding independent solutions will be e to the power p1x cos q1x, x e to the power p1x cos q1x, e to the power p1x sin q1x, x e to the power p1x sin q1x. So we will write the general solution in this case as follows. So d4 plus 32d square 256, suppose this is equal to 0, d4 plus 32d square plus 256y equal to 0. So the auxiliary equation will be m4 plus 32m square plus 256 equal to 0. Let us, this is equal to m4 plus 6 m square plus 16 whole square equal to 0. Okay. If you square this, we get m4 plus 32 m square plus 256 equal to 0. So, we have here m square. Now, m square plus 16 is equal, gives you equal to 0, gives you m equal to plus minus 4i. Okay. So, plus minus 4i occur twice, because here we have m square plus 16 square. So, this gives you m equal to plus minus 4i and plus minus 4i. So, 4i occurs twice and minus 4i also occurs twice. So, here we will have the independent solutions will be e to the power, if p1 plus iq1 is a root, okay, and p1 minus iq1 is a root, then we have e to the power p1x cos q1x. So, we have here p1 is 0. So, cos q1x means cos 4x is a root, okay, sin 4x is a root, so cos 4x is a solution, sin 4x is a solution, and the other linearly independent solutions are x cos 4x and x sin 4x. So, we will write the general solution as y equal to c1 cos c1 plus c2x cos 4x and c3 plus c4x sin 4x in this case, where c1, c2, c3, c4 are arbitrary constants. So, with that we come to the we conclude this lecture on solution of homogeneous linear differential equations of higher order. I thank you for your attention.